Now we talk about writing KCL equations by inspection. But before that, a reminder. A reminder from our previous course, EC 251. Do you remember what is the inverse of a resistance? It was represented with the letter G. OG, that's right. It was the conductance, measured in Siemens, formerly in mode, an upside-down ohm. What is the inverse of an impedance Z? It's an admittance Y, another complex number also measured in Siemens or mhos, like so. A set of KCL equations for a circuit with 3 nodes like this one, right? 1, 2, 3 and the reference. But the circuit is irrelevant. We know we're going to have 3 KCL equations, one here, another there, and another there. Well, the first KCL equation has this general form. A coefficient, a number A11 times the voltage of the node V1 plus another number times V2 plus another number times V3, the voltage of the third node equals to a quantity, a number that depends on the current sources we saw previously. And this equation belongs to node 1. That's correct. That's why I will call V1 the host, while V2 and V3 are invited to the party of V1, KCL1. Those are the guests of the equation. This is the host, those are the guests. For the second node, we write KCL2. Again, we have an equation very similar to that one. Will be A21, a number, times V1, plus A22, V2, plus A23, V3 equals to a number. In this case, because the equation is of node 2, the host would be V2 and the guests would be the other nodes of voltages V1 and V3. That's right. Now for the third node, we write KCL3. In KCL3 again the equation has the same shape, a coefficient times V1 plus another coefficient times V2 plus a third A33 coefficient times V3 equals to an independent number. In this case, you tell me. Who is the owner of the equation? Of course, it's node 3. Who is the host? V2 is. Who are the guests? You got it right. V1 and V3. Remember the concepts. Host and guest. We are going to use them. All equations in one. So let's take the system of equations KCL1, KCL2, and KCL3 and write them in matrix form. We write a matrix of the coefficients of the unknowns V1, V2, and V3 and multiply them times the vector of unknowns like so. That is equal to the vector of independent terms. And we know how to enter this in the calculator and solve for V1, V2, and V3. Let's see what is the actual form that those coefficients A11, A12, A13, etc. take. We will learn how to write those coefficients by inspection of the circuit. Writing the matrix by inspection. Let's take the circuit I mentioned before. We identify the reference nodes 1, 2, and 3. 3 KCL equations. You see there is no evil branch, no controlling equation, no op-amp. The only thing left are KCL equations for the 3 nodes, 1, 2, and 3. Let's write it. I will just write them and then talk about them. For node 1, we have KCL1, a coefficient V1, a coefficient V2, a coefficient times V3, and then a number. And we have KCL2 and then KCL3. You can stop the tape and verify the accuracy of those coefficients. But here what I want to highlight is something. Observe that the coefficient of the host of the first equation, which is V1 is the host, is positive. The coefficient of the host of KCL2, which is V2, is also positive, and the coefficient of V3, the host of KCL3, is also positive, while all the coefficients of all the guests in every equation are all negative. Oh, that's interesting. What else? The coefficient of the host is always the sum of all the conductances connected to that node. Remember, conductance is the inverse of the resistance, right? Right. So the coefficient of the host of node 1 will be the inverse of 2 plus the inverse of 3 plus the inverse of 4. Observe, inverse of 2, those three inductances added together give me the coefficient of the host of KCL1. Let's find out the coefficients of the hosts of the other two equations for KCL2. The coefficient of the host is this, and that is indeed the sum of the conductances connected to the node 1 over 3 plus 1 over 6 plus 1 over 5. 1 over 3 plus 1 over 6 plus 1 over 5. Positive number. Let's go to the third equation, but I think you're getting the idea, eh? What is the shape of the coefficient of a guest? Well, the coefficient of a guest is going to be the negative of the sum of all the conductances joining the host to the guest. How's that? Well, here we're going to put the negative of the conductance connected between the host and the guest, between the 1 and 2. Between 1 and 2, there is only 3 ohms. The conductance is 1 over 3, negative 1 over 3. And what is the coefficient of this guest? The negative of the conductance between that guest and the host, between 1 and 3, 1 and 3, and that is 1 over 4, negative 1 over 4. You can check out all the guests' coefficients, all of them are negative, all of them are the conductance connected between the host and the guest in that equation, between this guest, node 2 and node 3, between 2 and 3, 1 over 5, 1 over 5 negative. That's why this matrix 2b is going to be symmetrical. This is the conductance between node 3 and node 1. This is the conductance between node 1 and node 3. Of course, this matrix is symmetrical with respect to the main diagonal. The right-hand side is the sum of all the current sources, currents entering that particular node. For node 1 is 10 minus 30 minus 20, just like that. For node 2, the current entering the source from current sources is just 30 amps. And for node 3, it's going to be plus 20 minus 40, like so. So you see that we can really enter that matrix directly from inspection into our calculator. Now you see that. How can we say that this is so? Imagine there is a generic node K that is fed by this current source IA, and this other current source IB that is actually sucking current out of that, and it's fed also by this current source IC. It is joined to node 1 by this resistance K1, and joins node 2 by this resistance K2, and it's connected to node N by the resistance Km. Let me say that I am assuming all the currents through the resistors as leaving the node. That does not represent any loss of generality, of course, as you well know. And I'm going to write the KCL equation for that node. KCL equation for that node. KCL equation for node K. Currents leaving the node through resistors will be Vk minus V1, Vk minus V1 divided by the resistance between those two nodes, Rk1, plus this other current, the current that flows from K to node 2, Vk minus V2 divided by the resistance, well, Vk minus V2 divided by the resistance between K and 2, and so on and so forth for all the other many nodes that there might be eventually until we come to this one. There may be many others, right? If this current is Vk minus Vm divided by the resistance that is connecting them, Rkm. And all of that is equal to the sum of the currents. Currents entering the node from sources is Ia minus Ib plus Ic. Let me write that. Ia minus Ib plus IC. Observe that the coefficients of the host voltage Vk, all those coefficients are not only positive, but are also the sum, all the conductances connected to the node as we had predicted. And the coefficients of all the guests are negative and are the conductances that join that particular node, guest node, to the host, as we had also anticipated. So this is a justification of why that inspection method of constructing the matrix of admittances work. And I use the word admittance, yes, because you could use impedances here as well and phasors for those current sources. What happens if we have V sources? As long as those sources are not evil branches, this will work. Why is that? Because they would be in a Thevenin branch. It would be a V source in series with a resistance. They would look something like that. A voltage source in series with a resistor, and we know pretty well that we can transform that branch into a Norton branch with a current source in parallel with a resistor with exactly the same value that we had before, RT, and the source would be VT divided by RT as we saw in EC251. The rest of the circuit is not affected. And now we can use the method that we've seen. Not if the branch is evil. If the branch has only a V source, we cannot use this inspection method. So we convert all of them to Norton branches. That is what we're going to do. What about if we have an RI branch? A branch that has only one resistor apart from a current source. We remember from EC251 that resistance does not appear in any KCL equation, right? Right, that resistor is doing nothing in the equation, so we treat that branch just as a line branch. We ignore. So if we have a branch that is like this one, a current source in series with a resistor, well, we treat that as if it was only the current source for purposes of writing the equations. Later on, we may need the power in that resistance or something like that. But to solve this circuit, we treat that branch like this. This is a very nice method. However, unfortunately, this technique works only if there are no evil branches. You know what that means. If no branch contains a solitary voltage source. If there are no controlled sources. Fortunately, very many circuits are like that in the electric power industry. So, in phasor analysis, we will be using this method a lot.